Okay, so we're going to talk about how to solve gas law math problems. I'm going to work through some examples for you. What you need is your calculator. You need your math problems, and specifically we're going to do 1, 3, 5, 8, 17, and 19. And you also need some paper so that you can write down and follow along with the steps that I'm doing. Before we start, I want to point you to the table that's up here. All of these equations are on your reference sheet. You'll get the reference sheet for quizzes and tests, but you need to have this handy when you're doing the math problems, when you're doing the work. Okay? So STP is standard temperature and pressure. Standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. We're going to have to convert our temperatures from degrees Celsius to Kelvin. And in order to do that, you need to add 273 to your Celsius temperature. Over here, you have your equalities for pressure. So 1 atm is equal to 760 millimeters of mercury, which is also equal to 760 torr, which is also equal to 101.3 kilopascals. In the middle, you have Dalton's law of partial pressure, and I'll talk about that when we get to problem number 17 or 19. And then along the bottom, you've got your regular gas laws. Okay, and I'm going to show you how to work these. So if we take a look at problem number 1, you have 1.00 liter of a gas at standard temperature and pressure. It's compressed to 473 milliliters, and you want to know what is the new pressure of the gas in atm. Okay, so what I like to do first is sort of assign variables to the numbers and the units that I have in the problem. Let the units do the talking for you. So liters is a volume, so I have 1 liter of a gas at standard temperature and pressure. Now these are just words, but they mean numbers. So standard temperature and pressure is STP. So the standard pressure is 1 atm, and the standard temperature is 0 degrees Celsius. This 1 liter volume is compressed, okay? That means the volume is decreased to 473 milliliters. So there's another volume. And I want to know what is the new pressure of the gas. So I want to know another pressure. All right, so I've got volume and pressure, and I've got it twice. Notice how I don't have temperature, so we're going to assume that this temperature did not change because I was not given a new value for temperature. So if I list my variables, ones and twos, ones mean initial, two means final. Okay, so my initial pressure is 1 atm, and at that pressure, my initial volume is 1 liter. Okay? I do not know my new pressure. That is what I'm looking for. So that's P2. And my new volume, my final volume, is 473 milliliters. However, I need my volume units to match so that I can cancel them out. So I'm going to convert these milliliters to liters. So that would be 0.473 liters. Okay? So the equation that I'm going to use that just has pressure and volume is P1V1 equals P2V2. Okay? I am looking to solve P2. I need to isolate that variable. So I need to divide, isolate means to get the variable by itself on one side of the equation with nothing else beside it. So since it's multiplied by V2, I need to do the inverse and divide it by V2. So V2 divided by V2 cancels that out, and now I have P1 V1 over V2 equals P2. And this is the equation that I want to use to solve for my answer. All right? So that is the unsubstituted but manipulated form of the equation. So now I'm ready to plug in the values. So P1, and if you go look back up here where you've written your variables, that will help you substitute. So P1 is going to be 1 atm. V1 is 1 liter. V2 is 0.473 liters. My liters will cancel, and I have a ATM, a pressure unit left over, and that's what I want because I'm solving for a pressure. So if you multiply the top and divide by the bottom to 368, you get 2.11 ATMs as your new pressure. Okay? All right, moving on, next problem. Problem number 3. Gas is collected at 130 kilopascals, so that's a pressure. The temperature decreases, so I've got a temperature. The temperature decreases to negative 78 degrees Celsius, and the pressure increases, another pressure, to 175 kilopascals, and I want to know what is the original temperature in degrees Celsius. Okay, so I want to know, it says original, so that means initial or beginning. That means T1. I want to solve for T1. So I've got P's and T's and nothing else. So I'm going to use this equation, this Stay-With-Sachs equation. P1 over T1 equals P2 divided by P. P2 divided by T2. List my variables. Okay, so a gas is collected at 130 kilopascals. So P1 is equal to 130 kilopascals. T1, I don't know. That's my question mark. The question was, what is the original temperature? P2 is 175 kilopascals. T2 is listed as negative 78.0 degrees Celsius. Okay? You need to be careful with this because when you are solving problems that involve temperature, that temperature has to be converted to degree or to Kelvin. So in order to convert degrees Celsius to Kelvin, you're going to use this relationship up here. So I'm going to take my Celsius temperature and add 273, and that'll give me a Kelvin temperature of 195. Okay? You have to do that before you do any substitution into an equation. If you try to solve using a Celsius temperature and then convert it to a Kelvin temperature, you will get it wrong. So please don't fight on that. Just go ahead and make your conversion as soon as you're setting up your variables. Okay? So, I need to write my equation. So I'm going to have P1 over T1 equals P2 over T2. When you have a fractional equation, an equation where you've got a numerator and a denominator, it's easier if you linearize that, okay? That means make it like a line, like a sentence. So if you cross multiply each side, you'll get P1 times P2, and I got that from multiplying these two variables, equals, multiply this side now, P2 times T1. Okay, so now my equation's a line. I need to solve for T1. So I need to solve for this variable right here and isolate it. You get it by itself. So divide both sides by P2 in order to isolate that T1 variable. That would cancel out P2, and now I have T1 is equal to P1 T2 over P2. Okay? So this equation is my unsubstituted but manipulated equation. I've manipulated, I've changed it around to solve for what I want. Now I'm ready to plug in my values. Okay, so pressure 1 is 130 kilopascals. Temperature 2 is 195 Kelvin. Pressure 2 is 175 kilopascals. And I'm looking for temperature 1. Okay? So kilopascals will cancel, and that's good because I'm left with Kelvin, and Kelvin is a unit for temperature. So when you solve for that, you're going to get 145 Kelvin. If you look back up at the question says, what is the original temperature in degrees Celsius? That does not mean solve the problem in degrees Celsius. That means take the answer that you get and convert it from Kelvin back to Celsius. So in order to do that, what we need to do is we need to say 145 Kelvin minus 273 will take me back to degrees Celsius. And if you say 145 Kelvin minus 273, that'll give you 128 degrees Celsius. And that is your final answer for your initial temperature. Always convert your degrees Celsius to Kelvin. And at the end, if you need to take it back to degrees Celsius, then convert it back to degrees Celsius. So don't ever try to work a problem with degrees Celsius substituted in your equation. That will mess you up, I promise. Okay, next problem. So we have 500 liters of gas are prepared at 0.921 atms and 200 degrees Celsius. So I have a volume, I have a pressure, and I have a temperature, and I know I'm going to have to convert that to Kelvin. The gas is placed into a tank under high pressure. When the tank cools to 20 degrees Celsius, so a new temperature, the pressure of the gas is 30.0 atms, a new pressure. So I want to know, what is the volume of the gas in liters under these new conditions? So now I have three variables. I have a volume, I have a pressure, and I have a temperature. I have another temperature, I have another pressure, and I'm looking for a new volume. So if you see on the top in the equation box, this combined gas law gives you all three variables in one equation. This problem isn't hard unless you don't set up the problem correctly, unless you're not organized. So you have to be organized when you're solving an equation that has 1, 2, 3, 4, 5, 6 different variables. Okay? So I'm going to list all my ones first. My ones are initials. So I have P1, B1, T1. Then I'll have P2, B2, T2. Initially, the pressure is 0.921 atm. Initially, at the beginning, the volume is 500 liters. Initially, the temperature at the beginning is 200 degrees Celsius. So I need to add 273 to this. So I'll have an initial temperature of 473 Kelvin. Initially, my pressure is, my final pressure is 30.0 atms. I don't know my final volume, that's my question. What is the volume? And I know that my final temperature is 20 degrees Celsius, so I'm going to add 273 to that, so it'll be 293 Kelvin. So I'm looking for V2. This is the first step, setting up your variables. Okay, then I'm going to write the equation. So I'm going to write P1, B1 over T1. P2, B2 over T2. I want to solve for this variable right here. I have to isolate it. And if you're given a fractional equation where you have a numerator and a denominator, it's easier if you linearize that. So cross multiply each side. So if I do this side first, I'll have P1, B1 times T2 equals, now do the second part, P2, B2, T1. I want to solve for V2, okay? I need to isolate it. It's multiplied by two variables, so I need to divide by two variables. I need to divide by P2, T1. If you do it to one side, you have to do it to the other. That cancels out P2, that cancels out T1. So now I have, I'm going to write it over here, sorry, now I have B2 is equal to, and I'm just looking right up here at the work I've done, P1, B1, T2 over P2 times T1. See how many variables that is? If you're not organized, it's going to mess you up. All right, now time to plug in. Okay, so the initial pressure was 0.921 atm. The initial volume was 500 liters. The final temperature, T2, And be careful, make sure I know both of these were 1 and 1, but this is now 2. So that T2 is 293 Kelvin divided by P2, which is 30.0 ATM. And your T1, if we look back up here, is 473 Kelvin. Okay? If I were you, I'd multiply the top, multiply the bottom, and divide the top by the bottom. Okay, so if you do the math on this one first, your ATMs will cancel, your Kelvin will cancel, and you're just left with liters, and that's what you want because you're dealing with a volume. So if you solve correctly, and we're going to 3 sig figs, our new volume is going to be 9.51 liters. Okay? And there's V2. All right, next problem. I have 325 liters of a gas. The volume decreases to 296 liters, and the temperature decreases to 14.8 degrees Celsius. And I want to know what was the original temperature of the gas. So I have a volume. I have another volume. Okay? I have a temperature in degrees Celsius. I'm going to have to convert to Kelvin. And I want to know what was the original temperature in degrees Celsius. So I'm looking for a T2. So I've got volume and temperature and nothing else. So I'm going to use this equation, that's Strauss law. Okay? So I'm going to list my ones. Remember, ones are initial, twos are final. So volume 1 is right up here. It's 325 liters. Temperature 1, we don't know. That's your question mark. Okay? Volume 2. Volume 2 is 296 liters. And temperature 2, all right, so what we need to do is we need to take this temperature, negative 14.8 degrees Celsius, and we need to add 273 to that. Okay? So 14.8 negative plus 273 is going to give you 258.2 Kelvin. Alright, so now I'm ready to write my equation. So V1 over T1 is equal to V2 over T2, and it's another one of those fractional equations, so linearize it. Multiply both sides, cross multiply each side so you get a line. So now I'll have V1, this side first, times T2 is equal to V2 times T1. I want to solve for T1, so I need to isolate it, get it by itself. So it's multiplied times V2, I need to divide by V2. Okay, that'll cancel that out. And now I have for my equation, V1 times T2 over V2 is equal to T1. Alright? So if I go over here now and plug in my values, you're going to have to, no, you're good. I have 325 liters for V1. I have for T2, 258.2 Kelvin. And for my V2, I have 296 liters. Okay? My liters will cancel. I'm left with Kelvin, and that's a good thing because I'm looking for a temperature. And I know it says what's the original temperature in degrees Celsius, but remember, I have to solve in Kelvin and then convert to degrees Celsius. So, 225. Okay, so I get to 3 sig figs, 283 Kelvin. And I need to convert that back to degrees Celsius. So I'm going to take 283 Kelvin minus 273 is going to equal my temperature in degrees Celsius. And then you just do 3 significant figures, so it's going to be 10.3 degrees Celsius is T1, is the original temperature. Okay? Alright, this next problem deals with something a little bit different from these bottom equations that we've done. I've given an example of Boyle's law. That was problem number 1. We just did Charles's law, which was problem number 8. And we did the combined gas law, I believe it's problem number 5. And Gay-Lussac was number 3. Okay, so now we're going to deal with Dalton's law of partial pressure. And what that says is if I have a mixture of gases, the total pressure of the mixture of all the different gases is equal to the pressure of each individual gas added together. Okay, so this A, this B, this C, that refers to the different gases that are in the mixture. So if I have a metal tank that contains 3 different gases, oxygen, helium, and nitrogen, and you should recognize that oxygen is O2, it's a diatomic molecule, it's brother Hundscliffe. Helium is monatomic, it's an atomic, monatomic gas. And then nitrogen, N2, is also diatomic. These 2 are your brother Hundscliffe elements. Okay, so the tank contains oxygen, helium, and nitrogen. If the partial pressures, that means the sum of all the individual pressures of the 3 gases in the tank, total 35 atms of oxygen, 5 atms of nitrogen, and 25 atms of helium, what's the total pressure? Okay, so oxygen has a pressure of 35 atms. Helium has a pressure of 25 atms. I did this out of order, sorry. And nitrogen has a pressure of 5 atms. So the sum of the pressures of all of these gases should add up to the total pressure. So P total is equal to the pressure of oxygen plus the pressure of helium plus the pressure of nitrogen. So I have 35 atms plus the helium is 25 atms plus the nitrogen is 5 atms. So if I add those up, I will get the total pressure at 65 atms. So the individual pressures of each of those gases added up to the total pressure is 65 atms. Okay, and the last problem I'm going to work is a more simplistic one where you're using these equalities. So I have air pressure in the tire as being 109 kilopascals, and I want to know what's that pressure in atmosphere. So I want to convert from kilopascals here to atmospheres here. 1 atmosphere is equal to all of these pressures. So this is not like GMP or your mole map where you have to hit each step. All of these equal each other. So I could take these 2 out and say that 1 atm is equal to 101.3 kilopascals. Okay, so I'm going to start with my given. 109 kilopascals. And I want to go from kilopascals to atms. So atms is what I want to go to. Kilopascals, what I need to get rid of. And if you look at your relationship at the top, 1 atm is equal to 101.3 kilopascals. So your kilopascals will cancel, and I'm going to 366 with this because my original given pressure was the 366. Okay, so 109 kilopascals divided by 101.3 is going to be equal to 1.08 atmospheres of pressure. And there you go. If you didn't understand part of this, I'm going to put several other videos on Edmodo for you to follow, but it is imperative that when you come to class on Wednesday, you have watched this, because I'm not going to do any guided practice. Our time is limited, and you need time to actually do the practice. without me standing up and doing and watching. Because as you can see, this has taken 25 minutes of your time, and we're in a 47-minute period. So it's very important that you watch this and that you write down the steps that I use to solve. So I would watch the video again if you need to, and then try to do the problems without watching the video. If you want to go ahead today or this evening and do the sample problems, the ones that I did not do, then keep going, because we're just going to do that tomorrow in class. All of these problems 1 through 23 are due on Monday, November 14th, and you'll have a quiz on these problems on Tuesday, November 15th. Please do not get behind. Let me know what I can do to help you, but please do not wait until the last day. Thank you so much for your time.